Good morning, and thank you for coming. It's nice to have a full house. My name is Peter Behrendt. This is panel number 3205, our blue planet from the vantage of space. I'll introduce our speaker in a moment. This is one of two venues at CWA where the presentation is being streamed, and if you wish, you have an option to ask questions by texting, but please do turn down the volume on your phone so we don't get ringing. In order to do that, you have to first disconnect from any previous use of the cell phone, or your questions will go to the wrong place by clicking leave. To join the session, you have to text to number 37607. You will get a message saying you're online, and then you can reply to that message with your question to the panel. If you don't want to do that, and I suspect most of you don't, we have two producers, if they would raise their hands. One there and one other. If you have a question, you can raise your hand and they will bring you a card and a pencil and you can submit your question in writing. No videotaping, please. And please turn down the volume on your phones. I have had my own experience with an ocean years ago. I took a potential girlfriend from Nebraska to see the Pacific, and she looked at the distant horizon and said, it's not as large as I thought it would be. And I decided right then and there this was not the girl for me, but our speaker would have been ideally positioned to explain to her that it's rather quite large. Eric Lindstrom is an executive at NASA headquarters in Washington. His scientific interests include the circulation of the ocean and the air-sea exchange. And one of his current missions in life is to get NASA to look not only out into space, but down onto Earth, which I believe is a relatively small portion of their budget and their effort. Eric, it's nice to have you here.
Thank you very much. Yes. NASA has a big part in looking back at the Earth. 10% of NASA is spent looking back at the Earth, and NASA's budget is $20 billion, so $2 billion goes towards Earth observing. So I'm going to give you a small slice of Earth observing from space today, and really it's more about my love of the ocean and telling you about the ocean rather than the space technology. So I'm hoping that all of this technology will work. This is a 5-minute movie which will warm you up to oceanography from space, and then I'll get started. And there should be sound. Is there sound? No. Okay, maybe I need to narrate.
Did you guys do a sound check at all? No. Okay. put a microphone on the speaker here?
Okay, we're doing the old-fashioned way. Yeah, we will.
Earth is the water planet. Although 40% of Earth's population lives within or near coastal regions, the ocean impacts people everywhere. Most of Earth's water is stored in the ocean, a driving force for weather and climate. The Earth's surface is warmed unevenly by the sun. Heat, a form of energy, helps drive ocean and atmospheric circulation. The ocean absorbs and stores more heat than the atmosphere. Both the atmosphere and ocean move heat. The atmosphere does this quickly, the ocean slowly. At the ocean's surface, winds drive currents. Multiple forces keep the global ocean conveyor belt, or thermohaline circulation, in perpetual motion. Below the surface, deeper currents are driven by differences in density. Mixing and upwelling in the ocean transport nutrient-rich waters to the ocean's surface. Nutrients sustain biological productivity in the ocean. Extreme variations in sea surface height and sea surface temperature affect ocean and atmospheric circulation. El Niño and La Niña occur when changing wind patterns displace warm and cool water in the equatorial Pacific. Both have global impacts. During either of these events, the replacement of cold water by warm water leads to air temperature swings and changes in humidity. This alters weather patterns by steering storms and rainfall to new locations. Shifts in rainfall affect plant growth in areas impacted by drought. When heat is exchanged between the ocean surface to the atmosphere, it influences climate. For example, heat and moisture carried by the Gulf Stream northward bring warmer temperatures and a moderate climate to Europe. An eddy is a circular moving body of water that spins off a main current. Eddies play a major role transporting heat and nutrients. Thunderstorms are a frequent occurrence in the tropics. Some of these may become organized into large rotating systems with strong winds growing into tropical storms or hurricanes. Tropical ocean basins like the Caribbean and the Gulf of Mexico retain substantial heat, making these regions favorable for rapid storm intensification. By extracting large amounts of heat from the ocean, storms can become massive and destructive hurricanes. A driving force for weather and climate. The ocean is essential to life on Earth. It is the primary storehouse of Earth's water. Without the ocean, our planet would be uninhabitable. NASA satellites and their unique view from space are helping to unveil the vast and largely unexplored ocean.
Thanks very much for coming this morning. I thought this little 5-minute pre-produced version would give you all the summary of the ocean, and if we got short on time, you'd have at least gotten the high points. So I will do my best to now delve in a more geeky way to the three subjects: sea level in the ocean, the ocean's role in the water cycle, and plastic pollution in the ocean. So it is our planet, blue planet. Some people call it Earth, but I think it should be called ocean. I'm not the first person to have thought of that. It's the ocean gives us much in the way of food, minerals. It's 90% of the goods that you wear. The underwear you're wearing right now came across the sea on a ship. I can guarantee it. We're getting more energy from the ocean in wind farms. There's lots of energy stored in the vertical temperature gradients in the ocean that could be mined in rather benign ways. So, we have this impact on the planet. All the people, the rapid growth of population, our energy use, puts lots of carbon dioxide into the atmosphere. We have agricultural runoff, bringing nutrients into the ocean. The offshore oil and gas industry has occasional disruptions, which lead to major pollution events, and so on. So the ocean is under threat and pressured. And so we have this balance that it gives us a lot, and we expect it to take a lot of abuse from us. NASA is much more than these Mars missions. We have in the NASA's mission is to protect and understand our home planet. And here's the most NASA technical bit of the program. These are our Earth observing satellites as of middle of last year. They're acronyms flying around the planet. It's a lot cheaper to launch acronyms than actual satellites. So these are just our Earth observing satellites. At any one time, NASA has about 20 satellites on orbit observing the Earth, and about 20 in preparation, in building, planning, and so on. So I have, I'm a program scientist for 7 of the NASA satellites that observe the ocean right now, or are in preparation. So they go back as far as the QuickScat, which is still operating, launched in 1999. And I'm program scientist for a mission for measuring sea level, which launches in 2021. Typically from concept to launch to observing to death, it's about a 20 to 25 year cycle for a satellite. So you devote your career to 1 or 2 satellites and you're done. They have various orbits, and I won't go into all the details of that. So there are special orbits for special measurements to measure sea level. We have to go into a special orbit so we don't mix up the tides with the circulation. When we're measuring salinity from space, which is a real chore, we have to be flying right on the terminator between the light and the dark. So we can only measure salinity at 6 a.m. or 6 p.m. It's a wonder of nature. So it's getting hot in here, not just in here, in the ocean. 90% of the greenhouse gases, 90% of the heat from our greenhouse effect go into the ocean. Another probably 3 or 4% go into melting ice. Very little, a very small percentage goes into warming the atmosphere. So that's why you don't feel so much global warming, you know, actually feeling it, because the ocean's feeling it for you. It's one of those benefits of the ocean. This is the sea surface temperature, which we get daily on orbit and can make these nice maps. I wanted to try and, you know, point out some of the features on these maps, get geeky about tropical instability waves. You can see the equator from space because it's got special dynamical characteristics. For ocean water, it's kind of like a wall because the vertical the horizontal components of the Coriolis force from the spinning planet go to 0 at the equator, so it has very special dynamics. And there are special waves that only live on the equator, and they cause all sorts of interesting phenomena. So this warming is going on, but we also have please don't stop. Okay, thank you. As I said, CO2, about half the CO2 that we put into the atmosphere goes into the ocean, dissolves in the ocean, and that makes the ocean sour, acidic, and that goes to dissolving carbon shells on organisms. Any organism that makes a calcium carbonate shell, it gets dissolved. Here's a very small microscopic snail shell, very common in the ocean. And this is what it looks like when it's in waters simulated to be the acidity of the ocean in 2100. It almost gets completely dissolved in a month and a half. Right now, reefs are under pressure from acid waters. The pH, the acidity of the ocean has increased 30% since industrial time started. So organisms feel that. It's not the kind of natural change in the ocean which would happen over millions of years. They can't adapt to these rapidly changing acidic waters, and it's affecting aquaculture, for example, in the Pacific Northwest. They have to measure the acidity of the water and very carefully monitor it so they don't get acidic ocean water into their intakes in their shellfish aquaculture industry. So another impact of global warming is the loss of the Arctic sea ice, which we also monitor from space, going back many years. And this graph is kind of not too dramatic for a while, and then you'll see all of a sudden that global warming really hits, and we start seeing the decline of Arctic sea ice. This just shows you the cover of Arctic sea ice over time, the minimum ice cover. And really what is more dramatic than the loss of cover of sea ice is that there's almost no multi-year Arctic sea ice left. it used to be a large component that was really deep and thick. So all that's left now is the ice that's formed every winter. We still have winters and seasons. There's still ice coming and going every year, but it melts back almost completely. It didn't used to melt back completely because there was lots of very thick multi-year ice. But the multi-year ice is really history now. So one of the things that's really interesting to measure from space is that we can measure the gravity field very precisely, and that allows us to see the changes of mass on the planet. So when the Greenland ice sheet changes by melting, we can detect this from space. We have 2 satellites that go around the Earth, and they feel the gravity field below them. They get closer together and farther apart, and with lasers you can measure that distance very to microns, and we can derive the gravity field from it on the Earth's surface. And these are the areas over the last, from 2003 onward, in the dark shades where we've lost mass in Greenland, and we're measuring it here in hundreds of gigatons per year. And I'll show you what that means in terms of sea level in a moment. But this isn't happening just in Greenland. Greenland is really melting a lot faster than Antarctica is because there's a lot of warm Atlantic water coming up into these tidewater glaciers along the east and west coast of South Greenland and melting. But the place that's most critical in Antarctica is called West Antarctica here, and you can see the big spot where there's a lot of melting going on. Again, it's the ocean coming up against the glaciers, pushing them back inland, and as the glaciers retreat from the warm water can get under the ice sheets and cause further melting because the land below the ice is below sea level. Because of the weight of the ice on it for so long, so it's fairly critical. This is where they think that a major ice cube could really fall off of Antarctica, the West Antarctic ice sheet, and that would cause a really dramatic change in sea level. So we monitor these things. It's my horrific job just to watch it happen. So here are what it means in terms of sea level for Greenland and Antarctica. We get about 3/4 of a millimeter a year of sea level rise from Greenland right now, and about 1/4 of a millimeter a year from Antarctica. So 1 millimeter a year from melting ice sheets. It's a total of sea level rise of 3 millimeters per year. I think the next slide probably shows that. No, this actually, I'll digress for a moment and show you actual sea level measurements. This is, since 1992, we've been measuring every 10 days the sea level on the planet very precisely, and you can put them all together in a movie. And what a very clever professor here at University of Colorado Boulder, now at Old Dominion University in Colorado, Ben Hamilton, took the patterns of sea level rise that we've detected since 1992 and found what the patterns are, and then used that to derive what the ocean might have looked like from 1950 onward, using all the tide gauge data. So a very a mathematical trick to use the patterns to fit the old data and so on. So it's a best guess of what the ocean was doing from 1950 to 1992. And then this movie, once it gets to 1992, is reality. You can't tell the difference between when that happens. But in this movie, you see there are these big red splotches in the tropical Pacific. Those are El Nino events. And then when it goes blue, those are La Nina events. You can see all the eddies in the subtropical oceans that carry heat from the equator to the pole. They're very important in the ocean circulation. There are El Nino-like events in the Indian Ocean, not so well studied. So you average all these things together, And you find out that sea level is rising at 3 millimeters per year, and that we get about 1 millimeter a year from the ice sheets, about 1 millimeter a year from the warming of the ocean. As the ocean warms, it expands and gets greater volume. And then the last millimeter a year is from mountain glaciers. So they'll all be melted in 50 years. You won't see a mountain glacier on the planet. They're toasted. So they're contributing to sea level now, but they will stop eventually. There's also limits to, the expansion of the ocean due to warming. That's not the real fear in sea level rise is the changes due to the ice sheets. If all of Greenland melts, it's 6 meters of sea level rise. 6 meters, covers most of Florida. So there are these lots of coastal cities need to be worrying about 1 meters of sea level rise, and the ice sheets can contribute very large amounts over time. The science is about when and how much, and we're still working on that. We are very proud of continuing the sea level time series of satellites since 1992, and we now we know that since 1993, since we started measuring, there's been 3 inches of sea level rise, and we have the satellites in the program to go out to 2030. So we need to measure this over the long term for the sake of humanity. So it's rising, the water's rising not the same everywhere. It's not like a bathtub. In the Western Pacific, it's rising faster. Over the last 25 years, it's actually fallen off the west coast of the United States. And that could reverse. A large amount of that could reverse with changes in the Pacific decadal oscillation and their climate events that can cause. So you shouldn't be surprised if all of a sudden California starts seeing rapid sea level rise. It's what the West Pacific has been seeing for a long time, but that situation could reverse. The ocean could kind of relax and the sea level would rise very rapidly off California. So I'm going to stop talking about sea level and talk about the water cycle on the planet. We evaporate and precipitate a lot of water over the ocean. 80% of the water cycle on the planet happens over the ocean. Many scientists who claim to study the water cycle just study rivers and snow and lakes, and it's all about the fresh water. But the water cycle on the planet is driven from the ocean side, so oceanographers are always at war with hydrologists and people who claim to study the water cycle while ignoring the ocean. So it's a pet problem. Yeah. So what's really great about the ocean is that it preserves what changes there are in the water cycle, where it's evaporating or precipitating, and it imprints it on the surface salinity of the ocean. So where there's places on Earth there's more evaporation than precipitation, these are the red areas in the subtropical regions, the salinity is high, and where it is blue, the salinity is low, there's more precipitation than evaporation. So basically that's the picture. There are issues with the ocean circulation, so that it's not exactly that easy. But we measure now salinity from space. This is a big deal. The most sensitive radiometer ever launched by NASA can look back and measure the microwave emissions from the ocean at like 10 centimeter wavelength, the same as your GPS or so on. And it's a very tiny, tiny signal. And we have this super sensitive instrument, and we can get salinity. But first, there's all these stars in the galaxy emitting at that same L-band radiation. So we have to subtract a map of the galaxy off the South Pacific to get to salinity. So we have a shimmering map of the galaxy which gets in our way. This is real NASA stuff. We love it. Yeah. Yeah. So on this, you can see the Amazon River plume comes out every year, and part of it goes north, and part of it gets retroflected back into the tropical circulation. Oops, I moved on. Okay, I need to move on because time is of the essence. So the water cycle in the ocean here, we're taking some of the salinity from high salinity regions, putting it in low salinity regions, moving water around the planet. And the ocean preserves the signal of all this. Here's the map of the mean circulation on the left with the dots of high salinity and the low salinities. Well, if you look at the 50-year trend of salinity in the ocean from all the salinity data that's ever been collected, it has the same red spots. Where the salinity is high, it's also trending to get higher. And where it's blue in the mean map on the left, it tends to be blue on the right in the 50-year trend map. So the salty places are getting saltier and the fresher places are getting fresher. And that's a fingerprint of an acceleration of the water cycle and global warming. So the ocean can tell us that. If you tried to look at the water cycle on the continent, you would never see that because people are always in the way of trying to measure the water cycle, managing their own water. But nobody manages the water in the ocean except a few oceanographers. We can't change the salinity. So the Earth is giving us these signals, which are really amazing. So this is a break. This movie goes for a couple of minutes. It's 4 months of winds over the North Atlantic Ocean, and it's got the sea surface temperature underneath it. It's really beautiful. It's kind of soothing to watch. Well, I guess if you're an oceanographer, I can watch it over and over again. But as you get on into August, you'll start seeing these big swirls in the wind. They're called hurricanes. And you'll see them in August and September swirl across the orange parts of the ocean there, the higher temperatures, and they vacuum up the heat, as you might suspect a hurricane would, and they leave long yellow trails, which are the cold wakes of hurricanes. And since we started measuring salinity from space, we can also see salinity wakes behind hurricanes. And so this goes to the air-sea interaction, the key role of the ocean in the water cycle. The ocean provides the fuel that makes the atmosphere go. Water vapor in the atmosphere comes from the ocean. It's what you get in storms, your precipitation, all of this. It all happens on this interaction between the ocean and winds, which we measure directly from space by measuring the little ruffles on the surface of the water. We average them over 25-kilometer boxes and get a couple of views on them. And so the direction of the ruffles on the surface give us the wind direction, and the strength of the ruffles tell us the wind speed. So we can get to within 1 meter per second, 2 knots of wind speed, and directions like 15 to 20 degrees. So we average all that up, and that's what you're seeing. These are real observed winds and real observed sea surface temperatures. And where are we? We're in August, so there's a hurricane coming right here. And you should see the big, that is some change there. So it's just its fuel is just sucking the heat right out of the ocean. There's another one coming right there. This one's got a good wake too.
Do you know which hurricanes these were?
I don't know. 2011, I think it is. Okay, I got to move on. I think there's just one more here, right there. I think we're about finished. Yeah. I need to shorten that movie. It's the end that's got all the drama. Okay. So this is another look from the atmospheric side. There are these things called atmospheric rivers that hit California and cause big flooding in California from time to time. So these are, sometimes it's called the Pineapple Express, or it seems like these streams of water originate in the tropics and then point themselves at California, the Pacific Northwest, and just deliver buckets of rain. Back at the end of the Civil War, there was a great flood in California, left Sacramento under 10 feet of water. An atmospheric river got stuck off California and dumped on the Central Valley. So there was there was a lake where the Central Valley was in California. I think it was 1865, around then. So there was nobody much there to get flooded out, luckily. But it could happen again. That's the worry. You know, it's just because it's not in our memory doesn't mean that it's not ready to happen. So all these things, sea level, winds, storm surge. I worry about, you know, big wind events, sea level events. The ocean is rising, ready to come up and bite us. The winds on the planet, we're creating more storms by increasing the water cycle. The storms are getting more powerful, so we'll have more Category 5 hurricanes. So all of these issues we really need to pay attention to. You cannot ignore the ocean going forward. We're using it as a dumping ground for CO2 and heat and so on, and it's nice to us for the moment, but it won't be nice in the future if we keep doing it. Okay, we'll move to plastics now. You got to listen to this.
Piece of wood, plastic, 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 plastic. This doesn't matter where you point it.
Well, as a sailor, I've always been aware of marine debris. Walking my dog on the foreshore at home, I'm always surprised how much there is. You couldn't possibly keep pace with it, trying to collect it.
The marine debris becomes blindingly obvious to you when you're near the areas of major population.
I think the most surprising thing for me has been the amount of debris we've seen very, very far from land. You know, in the Southern Ocean, I mean, we're basically as far from land as you can be. And I remember at one point we were watching some seals, and then one of the girls who's up the rig is like, "Oh, look at that seal. Oh, it's a seal playing with a plastic bag." Definitely makes you realize the impact we're having.
One thing that sailing around the world does is it makes you realize just how small our planet is. If we can sail all the way across the widest ocean in 2 to 3 weeks in our small boats, that means the ocean isn't that big and we need to protect our seas.
The ocean is a big rubbish. There is too many.
How people in the world can't treat the ocean with more respect is just fully beyond me.
If we can just bring out the message how dirty the oceans are getting. It's not funny anymore.
No, it's not funny anymore. So I go to sea, and this message was precisely the one that I wanted to deliver. You go as far as you can get from land and cities, and you watch the ocean go by, and there's still plastic. There's on average now 13,000 pieces of visible plastic in every square kilometer of the ocean. And over my years of going to sea from the late 70s onward, there's been this big change from seeing sea life being the majority of things you see to being plastic is the main thing you see. We've fished out 90% of the large fish in the ocean. So with the fish went the birds, and it's kind of dead out there, and it's full of plastic, and it's horrible. So yeah, the world is small, and we're messing with it. So what can NASA do about plastics and debris in the ocean? This was a background. This is surface currents derived from our sea level and wind measurements. Put them together, we can get the surface currents. It's a very pretty video. It was on the background in CNN when they were talking about the Malaysian aircraft disaster in the Indian Ocean, how to track things in the ocean. People come to NASA. All the Volvo racers come to NASA. We can give them the eddies and the winds and so on to get themselves around by the most efficient means. All the transport around the world, people use these same products to get the most efficient routing of ships around the world. So this is a background. I'm not going to show you more of it because we don't have time, but it's nice to sit and watch and explain some of the features of the ocean circulation as they go by. But we're running out of time, so I want to get to the end. And some of the more messages about plastics, where they go in the same red spots you saw on the salinity map. Those are convergence areas. That's why the salinity is high. Salty water accumulates there, but also the plastics accumulate there. So that's we know where the garbage patches are in the open ocean from first order oceanography principles. And there's a lot of stuff out there, and it gets smaller and smaller as the ocean breaks it down. So there's enormous amounts of microplastics now, which the fish are now eating. So if you might just see them in fish guts, it's 8 million metric tons is the latest estimate of plastic waste getting into the ocean. I heard a statistic the other day that by 2030 there will be more plastic in the ocean than fish by weight. This is we do simulations of debris. This is the Japanese tsunami debris and how it spread out. You take the ocean currents and then you add a windage on, whether something sits like a styrofoam sits up on the surface, feels a lot of wind, or something below the surface just feels very little windage. So these are the colors are the different windages of the debris. And you see from the simulation, and this was all verified by what you pick up along the beaches, that the high windage items went up into the Gulf of Alaska and the low windage items farther down the coast. And so we know the theory worked with the actual collection of Japanese debris and the predictions of when these waves of material would hit. This is from a NASA-funded investigation at University of Hawaii. Okay, so what have we discovered? What have we learned? My final messages here. The ocean is large, but it's finite. We're impacting the ocean. The ocean's really a great integrator of all of mankind's engineering of the environment. It's taken in the CO2, the heat, the trash, all of these things, and that can be a good thing. It's also a bad thing. So, yeah, all this, we're thankful to the ocean for absorbing all of our things and letting us live our lives, but there are these consequences, and I really worry about, and I wanted to kind of alert you to consequences. We need to conserve the ocean to help us out in the future. What can we do? All the recycling. You know, 80% of the plastic in the ocean doesn't come from people dumping it in the ocean from the ships. It comes from runoff from land. So it's everybody's waste needs to be disposed of correctly here. We need biodegradables, recyclables, and so on. We need to watch what we eat from the ocean. We need sustainable fishing. So all of these are issues that you can become aware of. There's plenty of information on the web. But we need to put a true cost on the carbon economy, like what it's doing to the ocean. We need to value recovering CO2 and plastics. If plastics were worth $5 a pound when caught, the fishermen would bring them back the same as they did the fish. And then that would clean things up. So we need to put a value on plastics in the ocean. move to biodegradables, as I said. So finally, I think the message I have is we can't manage what we do not observe. So that's where NASA, and I'm also co-chair of the Global Ocean Observing System, which is all the in situ measurements as well. And so I try and manage the planet, our ocean planet, by observing it and telling you about it and letting you deal with the policy and the consequences. Thank you. One more final message. Thanks to the workforce here at UC Boulder. You guys have a great oceanography program here, great professors, and so you have people to help you understand this right here.
I think, Eric, we are just about out of time. Fascinating presentation, and thank you for your very important work.
Thank you.